Hey gang, one of the major types of calculations that we're going to have to do is to be able to calculate the pH during the course of a titration. And we're going to need to get that pH at several different stopping points along the way. So next to me here, I have a problem ready to go. It asks you to calculate the pH of the following points in the titration of 10 milliliters of 0.1 molar hydrochloric acid. And then they have these 4 points listed. And the first one is before adding in any base. So the big question is, if your pH probe is sitting in HCl, how do you calculate that pH? Well, first of all, you need to remember what type of chemical HCl is. HCl is a strong acid, so it's a pretty straightforward process to calculate that pH. And let's start doing that now. Alrighty. So if it's just 0.1 molar HCl, it's a straight up calculation of pH since it does fully dissociate. The pH is going to equal the negative log of the concentration of hydronium. And since the mole-to-mole ratio between hydronium and H's in HCl is 1:1, I can just straight up use that 0.1. So the pH equals negative log of 0.10 molar. My pH at this point should be 1. So that's our first point on our titration curve. We have a pH of 1.0 at 0.1. All right, well, things are about to get a little bit more interesting because now we actually start the titration. So at point letter B here, we're going to add in 5 milliliters of 0.1 molar sodium hydroxide. Now I'm going to have two chemicals present on the inside of my container, HCl and NaOH. Whenever you have more than one chemical present, you need to think, is a chemical reaction going to happen? Yes, absolutely it's going to. Acids and bases still react the last time that I checked. So at point letter B, let's start off with the chemical equation. So now we have the reaction of HCl plus NaOH makes some water and some NaCl. Now I'm about to show you a trick. I wish I could have showed you this during first year, but it was a lot to take in all at the same time. Ordinarily, we would take down the information about the hydrochloric acid. We would have, the 0.1 molar of 10 milliliters, the 5 mils, 0.1 molar. We'd have to do 2 stoichiometry problems to figure out what the limiting reactant is. We'd have to figure out through another stoichiometry problem how much excess is left over, and then from that, somehow scrounge up pH. Well, we're going to cut down on a lot of that work. What we're actually going to do here is a variation of stoichiometry using the ICE method. Now, I want to make sure that one thing is dramatically clear right now. Using a single-headed arrow. ICE, we really shouldn't be using with this, but we're going to anyway. Anytime that you have a single-headed arrow, chemical reaction, and you want to apply the ICE method, please convert to moles. Do not use molarity. Molarity is used with double-headed arrow equilibrium. It's a whole different style of problem, but we can still use ICE with a chemical reaction. Let's convert our materials to moles. So liters times molarity will get you the moles. Our HCl will have 0.00010 moles. Well, actually, I think I put in one too many zeros here. 0.0010 moles. And then for our sodium hydroxide, 5 milliliters of 0.1 molar, volume times the molarity will get you the number of moles here. This is 0.00050. Now remember again, these are a number of moles, and this is going to be a chemical reaction. Is it pretty clear to see which one of these is the limiting reactant at this point? I think so. It's the sodium hydroxide. How much of it are you going to lose? All of it. That's going to set my change. So let's lose all of it, 0.00050 minus 0.00050, adding in 0.00050. All right, let's calculate. I will have no sodium hydroxide left over after we're done. I will have 0.00050 moles of HCl after we're done. That would have normally had to take 3 stoichiometry problems to get to, by the way. And I'll also produce 0.00050 moles of NaCl. Great. So that's it for our stoichiometry. But if you remember, we still need to calculate the pH. So at this point, you need to sit and think, what do I have present in my solution? I have a strong acid and I have a salt. Is this a buffer? No, it's not. A buffer is made from a weak acid and a salt with a common ion in it. This doesn't qualify. In fact, this salt is not even capable of changing the pH. Both the sodium and the chlorine ions are very stable in water. They won't re-react. But I do have HCl left over. That's a strong acid. Finding the pH of a strong acid is easy. We're going to take the negative log of the hydronium ion concentration. Now again, that's concentration. I have moles. One more step left. Divide by the total volume. What is that total volume, you may ask? Well, I had 10 milliliters of my acid, and I just added in 5 milliliters of my base. That's 15 milliliters, or 0.015 liters. That gives us a molarity of 0.0005 divided by 0.015. How about 0.033 molar? That's the molarity of my acid that's left over. Plug and chug. Let's plug and chug out a pH here. The negative log of that lovely concentration is a pH of about 1.5. So after the addition of almost half of the number of moles of that sodium hydroxide, I've only changed the pH by 0.5 points, which is kind of crazy. The pH stays very low for a very long time during a strong acid, strong base titration. All right, so let's calculate the next point. I don't think we're going to have too much trouble with this now that we've seen this new method. So now we're going to add in 10 milliliters of sodium hydroxide. Now that's to the 10 milliliters of the HCl. Do acids and bases react? Yes. Let's go to a chemical equation. Now again, if I'm going to use this ICE method, I must convert to moles. So if I have 10 milliliters of 0.1 molar, then this is 0.0010 moles of my sodium hydroxide. This is a pretty special point. If you'll notice, I have equal number of moles of my acid and my base. This would be stoichiometrically perfect. There's no limiting reactant here. I'm going to end up losing everything. So I'm going to lose 0.001 of my acid. I'm going to lose 0.001 of my base, but I will make 0.001 of my salt. So at equilibrium, no acid, no base, 0.0010 moles of my salt. I still need to calculate the pH though. So how is that done? If I don't have any of this, this is the only thing that might be capable, but both Na and Cl are both on those lists of being stable ions in water. They're not going to re-react with water. The pH is going to remain at 7. And one thing to say specially about this point, if I have equal moles of both acid and base, this is called the equivalence point. The only thing that you're ever going to have at the equivalence point is a salt. If you have a strong acid, strong base titration, then this salt is always going to be stable in water and it will never re-react. And your pH at the equivalence point is always going to be 7. Now that's going to change if one of these is going to be weak, but right now that's not the case. All right, so at point letter C, we finally see a rocketing high pH of 7. Only one more point left to calculate, and that's with the addition of 15 milliliters of my base. Let's see how that changes the scenario a little bit. 15 milliliters of 0.1 molar NaOH is 0.0015 moles. Again, the HCl and the sodium hydroxide, they are going to react. We'll need to put that into a chemical equation. This time, I'm adding in 0.0015 moles of my sodium hydroxide. My limiting reactant flips. It now becomes my HCl. I'm going to lose all of it. That sets my change. So after the reaction is finished, I'll have no more HCl. I'll have 0.00050 moles of NaOH and 0.0010 moles of my NaCl. So again, how am I going to calculate the pH of this solution? No more acid. I do have a strong base. And I have a salt. But we've already talked about the fact that this salt can't make a buffer because this is a strong base. And the salt is very, very, very stable in water. It doesn't re-react. This is the only particle that's capable of changing the pH. So I'm going to calculate it through pOH. pOH equals the negative log of the concentration of hydroxide. So I just need to transform my moles into a concentration before I plug and chug. So I'm going to divide again by the total volume. Total volume at this point, just to refresh our memories, 10 milliliters of my acid was added with 15 milliliters of my base. That's 25 total milliliters, or 0.025 liters. The molarity of my sodium hydroxide at this point would be 0.020 molar. I'm going to plug that directly into my pOH calculation. pOH is going to end up being 1.7, and I'm going to subtract from 14 to get to my pH. That looks like it's going to be a nice solid 12.3. So finally, last pH, 12.3. So I hope you enjoyed this new method of kind of doing some stoichiometry very, very quickly. Again, you can apply this ICE method, but when you have a chemical reaction and you're using a single-headed arrow, you use moles. If this was equilibrium and I had something weak in here, which would make it equilibrium, then you would have to switch back to molarity. But again, anytime that you're using a chemical reaction, just simply use a single-headed arrow, switch everything out to moles, and see what you have left over at the end.